Good morning. We begin with a quick recap of the lecture number 8 and the topics that we would like to cover today. We have already discussed about the properties of the upsampler. We have started to discuss about the downsampling process. Today we will complete the discussion in terms of the properties. We will look at several interesting examples. One particularly interesting example is the linear interpolation. Very often when you have to find a value between 2 points, the most natural thing for us to do is to do linear interpolation between those 2 points. Now, we use the word interpolation in that context. We have also used interpolation in our context where we insert zeros and do some filtering. Are they linked? Is there some insight that we can gain into the aspects of linear interpolation? And of course, one of the key things is we are not always limited to integer sampling rate change, either increase by an integer sampling rate or a decrease. Very often we are required to do a fractional sampling rate change. So that is a aspect that we want to focus upon, and then this leads us into some unique structures that are present only in multirate signal processing, not in traditional signal processing, which is what we refer to as the multiplexer and demultiplexer. You may think, well, I thought these things existed only in the communications domain. No, they actually exist in the multirate signal processing as well. So that is our goal for today. Let me start with a quick summary of what we have covered in the last class and build on that, and again if there are questions we will take them as they go along. So the block that we have looked at is the upsampler, where we insert L-1 zeros between successive pairs of samples. Every set of samples every pair of samples we will insert L-1 zeros. Now we showed that this is the spectrum or the Z transform of the expanded signal is related to the spectrum of the input signal by x e of z is equal to x of z power L. And again this we said introduces multiple images of the input spectrum, and just as a quick sketch of that, if this was the input spectrum, that you had a spectrum going from up to pi, then what you would get is the spectrum compressed. This would be pi over L. The next copy of the spectrum would be 2 pi over L, 4 pi over L, so on all the way to 2 pi. So basically we have got additional copies. This is copy number 1, copy number 2, the last one would be copy L-1, this would be copy L-1, and that is what would be x of z power L. And we said that if we followed the expansion of the signal by the zero insertion by a low pass filtering, which basically removed all of these images, then we get a interpolated signal. There are no more zero valued samples, all of the samples have been filled in, and the inputs, the resultant spectrum looks as follows. So you have limited to minus pi over L to pi over L all the way to 2 pi. So this basically says that if I had a signal which was band limited to pi over L, think of it as just some frequency, my Nyquist rate would have been 2 pi over L. So Nyquist rate would have been 2 pi over L, but actually I am sampled it at 2 pi. So which means I have sampled it at L times higher than Nyquist rate. So that is what the process of interpolation gave you. You got additional samples to make your signal look like it has been oversampled, and whether you interpret it by going into the continuous time domain or by remaining completely in the discrete time domain, you can still interpret it as a signal with a higher sampling rate and equivalent representation with in terms of the original signal. Now the other block that we have been discussing is the downsampling block, and the downsampling block indicated with the down arrow in terms of time is very easy to represent. X d of n is x of mn. The corresponding spectral representation or the Z transform or the Fourier transform representation, not as easy. We were in the process of developing it. Basically we defined an intermediate signal x1 of n which matched x of n at all multiples of m. otherwise it was 0. We said that that sequence is something that can be obtained by multiplying x of n with a comb sequence. Comb sequence is as defined as here. We use the roots of unity, complex roots of unity, to just construct a comb sequence, and then we were in the process of deriving the signal. So basically x1 of z, this is the point at which we ended the last lecture. I will pick it up from there. X1 of z we showed was 1 over m summation k equal to 0 to x of z w k. Now I just wanted to expand this a little bit. So if I write if I substitute z equal to e power j omega, then what I get is this term becomes x e power j omega. This, if you want to be precise, you can write a subscript m so that there is no confusion, but usually when we talk about it in the context of downsampling, and if the downsampling is by a factor of m, then we assume that the w term is defined with. So this would be e power minus j 2 pi over m into k. So this can be also written as e power j omega minus 2 pi over m into k, where k goes from of course 0 all the way to m minus 1. Okay. So here is where we see the shifted versions, and in today's lecture we will see this graph a few times, but let me just draw it. So supposing I had a signal that was band limited to minus pi over 3 to pi over 3. Okay, and I was basically doing m equal to 3, downsampling by a factor of 3. That is the case that we are looking at. Now what we are saying is the spectrum of x1 of E of j omega. So if I were looking at the spectrum of x1 E of j omega, will first of all introduce a scale factor 1 by 3. The spectrum for k equal to 0 is the original spectrum. Then k equal to 1, we get a copy of the spectrum shifted and centered around 2 pi over 3. And then for the k equal to 2, we get another copy of the spectrum shifted to 2 pi over 3, 4 pi over 3. Okay. So two copies of the spectrum, k equal to 0, 1, 2 will be the number of copies, and then you would have the original signal again. So this is what x1 E of j omega is. It has multiple copies of the input spectrum shifted by multiples of 2 pi over m. Okay, multiples of, they are centered around the frequency, and this here is a case where we saw this is this corresponds to k equal to 1, this corresponds to k equal to 2. Okay. So this is easy to visualize. So having visualized this, then it is just a very, very simple step to go from there to the downsample signal, because we already know the following relation: xd of z, spectrum of the downsample signal, is x1 of z power 1 over m. Okay, this we derived in the beginning of the last lecture. So it is nothing but a scaled version, or we call it a frequency stretched version of the input of the signal x1 of z. So this can then be written as 1 over m. Please pay careful attention to the substitution of the variable z power 1 over m. So wherever there is z, I am going to replace it with z power 1 over m. So which means that there is a scale factor 1 over m summation k equal to 0 through m minus 1. X is the first place where I am encountering z, and the only place where I will encounter z. Z replaced by z power 1 over m, and whatever is the argument multiplied by omega w m raised to the power k. So nothing else changed, only this happened. Okay, so this is my expression for the downsampler. Now very often when we go directly from x of z, so basically if you go from x of n all the way to xd of n, which will then mean that you are looking at xe of j omega, the spectrum of xe of j omega, from that downsampled version xde of j omega. There is all sorts of confusion, okay, because you do not know where the scaling is occurring, where the shifts are occurring, but what we have shown is that if you define an intermediate signal x1 of z, then it is very easy for us to construct what x1e of j omega looks like. x1e of j omega is the original signal with shifted copies at multiples of 2 pi over m, easy to construct. Now, the last step is when I want to construct the downsampled signal, we know that this relationship xd of z equal to x1 of z power 1 over m is nothing but a rescaling of the frequency. So, which means that whatever was the original frequency, I strike it off and then multiply it by the factor m. So, this, if I can cancel this and call it as pi, because in this case m is equal to 3. This one I will cancel and call it 2 pi, okay, that is it, to 2 pi. After that the spectrum will repeat. So, therefore, as far as xd of z is concerned, for this particular example, it is as follows: height of 1 over 3, height of 1 over 3, this is pi, and I have this as my copy, this is at 2 pi. Okay. So, that is it, that is the downsampled signal, the spectrum, absolutely no confusion. The 4 to keep in mind when we write down the downsampled signal: first of all, amplitude scaling. 3 of these were also observed when we were writing down the spectrum of x1 of z. So, I will just repeat that. One is the amplitude scaling, this was already present in x1 of z. The copies of the inputs of the signal spectrum, how many copies? M minus 1 additional copies, and the frequency shifts. So, all of these were present in x1 e of j omega, the scaling, multiple copies, and the frequency shifts, which is what we saw. Now, the last step of writing the spectrum of the downsample signal basically boiled down to doing a scaling of the frequency, rescaling of the frequency, that is all, rescaling of the frequency. Okay. Once you have this picture, then it is very easy for us to work with the downsampler and not have any confusion at all. So, the downsampling process, always my recommendation would be is think in terms of an intermediate signal x1 of z, which is the input signal multiplied by a comb sequence, which will give you this spectrum, shifted, scaled, shifted, multiple copies. Then the last step of getting this the spectrum will be just the requirement that you have to rescale the frequencies and make sure that you are looking at a period from 0 to 2 pi. Okay, any doubts on the notation that we have used? Okay, now we will spend a few minutes on an example which may seem like it is a little bit repetitive, but again look out for those things which will help you make sure that you will never have a doubt or a confusion whenever it comes to downsampling. So, here is the first a series of figures, probably easier for you to draw on your notebooks, but let me do the best that I can. So, the first one is I am going to draw the spectrum of sampling at Nyquist rate. Okay, again keep in mind that this is a series of figures, preferably draw it all on the same page. So, then you get the, so Nyquist sampling rate, the spectrum looks like this. This is 2 pi. Okay, so that is this is pi, Nyquist sampling rate. So, there is no gap in the spectrum, basically you are sampling it exactly at the twice the highest frequency content, and therefore, basically the two copies of the spectra just touch each other. Now, of course, reconstruction or removal or anything else you want to do with this is no. So, next one which I want to look at is sampling at 3 times Nyquist. 3 times Nyquist. Again, let me just quickly draw this picture. Okay, if this is pi by 3, minus pi by 3, this is pi, this is 2 pi, and this is the copy of the spectrum going from 5 pi by 3 to 7 pi by 3. Okay. So, basically this is a case where you have oversampled. If you had oversampled at 3 times the Nyquist rate, this is the spectrum that you would have observed. Okay. Now, take this signal, one that has been sampled at Nyquist rate, 3 times Nyquist. So, which means that if I go down by a factor of 3, take this signal, pass it through a downsampling by a factor, this is downsampling by a factor of 3, then I should not have any aliasing, because I actually did oversampling by a factor of 3 to begin with. And so, and we should verify that whatever we have done. So, downsampling by a factor of 3 first of all says get me the shifts of the spectrum, right, intermediate signal. So, first thing is to draw the shifts of the spectrum. Again, this is a repetition of the figure that we drew in the previous page. So, that is corresponding to k equal to 1, this corresponds to k equal to 2, the 2 shifts, the scale factor of 1 over 3, then the last step will be the rescaling of the frequency. This becomes minus pi, this becomes pi, this becomes 2 pi. So, the new spectrum for the downsampled signal, draw that in red, downsampled signal basically goes back to the original spectrum, it goes all the way to pi, 2 pi, but there is a scale factor of 1 by 3 which came in through the process of the downsampling that we had we have incurred. Okay. Now, for the benefit of clarity, would like to look at the same downsampling by a factor of 3. However, the input spectrum is not at Nyquist rate, but slightly is less than Nyquist rate. So, basically look at this particular scenario. So, I am going to redraw a spectrum which I would like you to look at and study for the downsampling. So, this is from minus pi over 6 to pi over 6. Now, what would this signal look like if I sent it through a downsample? Of course, there will be a repetition at 2 pi, right. What would happen to this signal if it were downsampled by a factor of 3? So, if this signal downsampled by a factor of 3, what would it look like? I would have to create multiple copies at 2 pi by 3s and 4 pi by 3. Please go ahead and do that. So, basically 2 pi by 3, 4 pi by 3 copies of this spectrum, okay. And then you would do a scaling 1 over 3, scaling of 1 over 3, and then you would do a rescaling of the frequencies. So, this would become multiplied by 3 will become minus pi by 2, this will become pi by 2, and this will become 2 pi. So, the spectrum of this signal after the downsampling process looks like this. It goes from minus pi by 2 to pi by 2, minus pi by 2 to pi by 2, there is pi, 3 pi by 2 and 2 pi, and of course, the downsampling did not of course have brought the images closer to each other, because previously they were further apart, but and it looks like there is a stretching in frequency, and we know exactly where the stretching comes from. Now, all of this was done to answer the following question. Now, if I gave you a spectrum that had the following form, where the signal spectrum went from 0 to pi by 2, minus pi by 2 to pi by 2, okay. And of course, that means the other copy of the signal would be here, okay. Now, if I took this signal and then downsampled it by a factor of 3, what happens? Okay. So, first and foremost I have to look at the shifted versions. Once you look at the shifted versions, then you do the rescaling. So, the shifted version says there is a copy at 2 pi by 3. So, 2 pi by 3 there is a copy, at 4 pi by 3 there is a copy, and of course there will be a rescaling process. Okay. So, if I were to after the rescaling, if I were to draw the new figure, then it would look like this. It will go all the way to 3 pi by 2, because pi by 2 will go to 3 pi by 2 and it will go to minus 3 pi by 2 on the other side, minus 3 pi by 2, and the copy of the signal or the other portion of the spectrum will start at pi by 2 and then go up to 2 pi. So, starts at pi by 2, goes all the way to 2 pi. Okay. So, the spectrum itself I have been able to reconstruct 1 by 3. Now, if you have come this far, then the next step would be okay. So, I will just zoom in and draw this figure. So, this is pi by 2, pi, 3 pi by 2, 2 pi, spectrum, copy, the other copy of the signal, and basically if I look at a composite signal, that is basically I have just drawn it. So, the signal itself will look like this. It has a scale factor like this, and then in this portion it is some combination of the green and the blue, and then it will repeat itself. Okay. So, this is 0, this is pi by 2, this is pi, 3 pi by 2. I think I have to redraw the red line and the blue line. 0 to 3 pi by 2, it goes to 2 pi. This is 2 pi. Okay. So, the other copy of the signal is from pi by 2 to 2 pi and then repeat. So, the copy of this, the resultant signal looks something like this. Okay. So, it has some resemblance to the original signal, but in the part where there is overlap, really we cannot say anything, because the two the copies have overlapped, and therefore, to interpret this signal we can say that yes, the original signal had a very clear band limited nature, but now after this process the one that I have has something like this. It has got some distortion, that especially towards the high frequencies. Now, what exactly happened? This is where this is the region where aliasing is occurring, and the spectrum where there is the portion of the spectrum where there is overlap is a place where, because of the aliasing, we may not be able to recover the original signal. If you were to now look at these three examples, okay. So, I had a case where the signal was limited to pi over 3. I did the downsampling, it was clean. Oversampled the signal, downsampled, of course there was no issue. When I exceeded pi by 3 and I went all the way to pi by 2, downsampled it, I saw that there was a aliasing that happened. So, here is a layman's way of describing the signal. So, when you do the downsampling, the following 4 steps happen. One, there is amplitude scaling, there is shifted copies of the spectrum. So, that is 2 and 3, shifted multiple copies of the spectrum, shifted by multiples of 2 pi by L, and the last one is rescaling of the frequency. And the rescaling of the frequency we described in layman's terms as a stretching of the frequency. Now, basically what we can say about the occurrence of aliasing is that rescaling will happen when I do the downsampling. So, if my rescaled spectrum, if the rescaled spectrum crosses omega equal to pi, then I will be having the effects of aliasing. Why? Because the next copy is going to be centered around 2 pi, this initial spectrum has gone beyond pi. So, when I shift it, there is going to be overlap between these two copies of the signal. In other words, rather than talk about the rescaled spectrum, you can also make the statement in terms of the original spectrum. So, if the input spectrum before rescaling means that if the input spectrum crosses pi over m, then when I do downsampling by a factor of m, aliasing will occur. Aliasing will occur. Okay. So, we have talked about it completely in the discrete domain. We remember not gone into the continue to why aliasing has occurred. Basically, we have shown that the input signal is periodic. When I do the downsampling, there is amplitude scaling, shifted copies of the spectrum and a rescaling of the frequency. And we have shown that if the input spectrum has content beyond pi over m, then the downsampling process will introduce overlapping of images. This overlapping of images is very similar, in fact is exactly the same as what happens when you undersample a band limited signal. There will be overlap of the copies of the spectrum, but this is not overlap of the continuous spectrum, but in the discrete domain itself we have shown that there will be overlap of spectrum. I may not be able to recover the original signal, which is what typically the description of aliasing. So, just to summarize, the downsampled signal x d of z can be written as 1 over m summation k equal to 0 to m minus 1 x of z power 1 by m, that is where the frequency scaling occurs. Now, if you go directly from x of z to this expression, there is always this confusion, do I scale by m, do I stretch by m, what happens to the shift, all of those doubts will occur. But if you go through this intermediate step, can avoid that confusion and be very clear in your mind what exactly is the spectral interpretation of the downsampling process. Okay, so now let us build on this for a few more minutes while we have that. So, let me make the following statements. So, to avoid aliasing, that would be one of the important things that we would want to do in multi-rate signal processing, because aliasing is a non-linear distortion, removing it is not easy. So, therefore, we want to be careful. So, one of the things that we would do to avoid aliasing is to pass my input signal through a ideal low pass filter minus pi over m to pi over m. In that case, I am guaranteed that there will not be any signal beyond pi over m, and then when I pass this signal through a downsampling by a factor of m, then the output spectrum before we do the rescaling, because I have only pi over m, then remember there will be shifted copies at 2 pi over m, at 4 pi over m and so on all the way to 2 pi. Okay. Now, after doing the rescaling, then what we have is something that goes from 0 to pi, this is pi 1 over m. Okay. So, that is the spectrum. If the input spectrum, signal spectrum is band limited to pi over m, that is an observation. If input signal spectrum as we have shown is band limited to pi over m, that is omega c is less than pi over m, that is the cutoff frequency that you have used, or whatever is your band limit of your signal, either through the band limiting process of the filter, then there is no aliasing. Okay, a very important result. And just like we used an anti-aliasing filter in the process of sampling, what did we do? We used an anti-aliasing filter to make sure Nyquist property would be satisfied. This is exactly the digital version of the anti-aliasing filter. So, this is the anti-aliasing filter. So, it is very intuitively very satisfying to see that whatever we understood from the aliasing, occurrence of aliasing in continuous time when we sample the signal, that same thing is also present when we do sampling rate conversion in the digital domain. Okay. So, which basically no aliasing after downsampling by m. One very important observation at this point is that, first of all, this is a sufficient condition, right, because we are saying that anytime you give me a signal that is band limited to pi over m, I downsample. So, clearly this is a sufficient condition, because we have not put any conditions in terms of satisfying. The minute you tell me spectrum is the band limited to pi over m, this result holds. So, it is a sufficient condition. Question is it a necessary condition as well? Necessary condition as well. Are there cases where you are not band limited to pi over m and you still do not incur aliasing in the process of downsampling? And the answer is yes, that occurs with band pass sampling. Okay. So, basically it is not a necessary condition. However, you can qualify it by with the following statement, that if you are dealing with for baseband low pass signals. Okay. So, for BB stands for baseband or low pass signals, okay, signals of the type that we have shown, low pass signals, it is a necessary and sufficient condition. If it is a low pass signal, it has to be band limited to pi over m, otherwise you will run into aliasing. So, it is a necessary and sufficient condition, okay, necessary and sufficient condition. On the other hand, if you are dealing with band pass signals, for band pass signals, that means you do not have a signal content all the way to the low frequencies. For band pass signals, it is a sufficient condition, it is not a necessary condition. For band pass signals, it is only a sufficient condition, it is a sufficient condition. Okay. So, very important. Maybe another way of visualizing it is as follows. The way to look at it is, look at just on the frequency axis. On the frequency axis, here I have pi over m, 2 pi over m, and so on, right. Now, before stretching, if this is the spectrum, after stretching 2 pi over m will go to 2 pi, right. This is this is after stretching. After stretching, and this is the if this is what we refer to as the sampling frequency after the down conversion process. Okay. Now, the same frequency before stretching is this one. So, this is the sampling frequency, or what corresponds to the sampling frequency before we have done the stretching. Before we have done the stretching. Okay. And if 2 pi by m is my sampling frequency, then my input signal better be limited to pi over m for Nyquist rate to satisfy Nyquist rate. Okay. So, again you can visualize it in multiple ways, whatever is the way that you are comfortable with, that I would recommend you to do that. Okay. Very quick question, a very quick example of what of something that translates into the exact same scenario that we have looked at. So, consider that you are looking at speech data which has spectrum in the range 0 to 5000 hertz. Okay. So, spectrum frequency, continuous time frequency is 2 pi times 5000. Now, the sampling frequency Fs is equal to 7500 hertz. Now, clearly this would be a case where you are not satisfying the Nyquist criterion. Now, what portion of my spectrum, what portion of the input signal spectrum is free from aliasing? Aliasing will occur, it is going to affect some portions of my spectrum. Which portions of my input signal spectrum is free of aliasing? Okay. And maybe it's you are seeing it right away, but please do draw it and make sure that you are comfortable with it, is free of aliasing. And you should find that the answer comes out to be 0 to 2500 hertz is the portion of the spectrum that is free of aliasing. After the process of sampling, what is the highest frequency content in your signal? Now you may say, well, why you ask me the question? There is frequency content all the way to 5000 hertz. Wait, that was before you sampled. After you sampled, if 7500 was your sampling frequency, it is 3750. What happened to those frequencies above 3750? They got aliased. And now which portion of the aliasing, which portion of the spectrum they affected? They happen to have affected from 2500 upwards of the spectrum. So what is the highest frequency component? Okay. Okay, please make sure that you are comfortable with these two results, and basically this corresponds to the case where you have a spectrum, digital spectrum all the way to pi by 2, downsample by a factor of 3. And I think this is an example we have looked at in the course of today's lecture, where we said that yes, there will be aliasing and what portions will be affected, and this exactly maps to that if you work out the details. Okay. So let me stop here.